All right, grade 12s. Well, as promised, I was going to explain the projectile motion to you in just a quick video here. This is a review of what we did last year. Now, before I show you this, I wanted to show you this little applet here. Okay, so if you take a look at what you're seeing here on your screen. Okay, how does projectile motion work? Well, basically, we use the component method. Now, if you don't remember that from last year, it goes like this. If I launch this projectile, so here I'm gonna launch it, okay? And as you can see, this cannonball sort of flies across the sky. I'm gonna reset it, okay, in a moment. But it follows this blue line, which is a parabolic arc. I'll just sort of trace it out with my black pen here. It follows that parabolic path, and we have equations for motion that describe the shape of that path, basically, okay? Now all we have to do is break it into components. Now I'm going to reset this. I'm going to erase the line, erase my line. Okay, and what I'd like you to do, I'm going to play it again. I've turned on the velocity vectors so you can see the two components. There's two components to the cannonball's motion, a horizontal part and a vertical part. And what I'd like you to do is just observe those two components and how they behave as the cannonball moves across the field. Okay, so watch. I'm going to launch it, and I'm going to pause it right there. Okay. Now, if you look at these two vectors, there is a green vector that represents Vy, the vertical velocity of the vector, of the cannonball. And then there's Vx, which represents the horizontal velocity of the cannonball. Okay. So those two components, Vy and Vx, are the two velocity vectors that are present as the cannonball moves its way across the field. Okay, now I'm going to continue to play this. Now here at a different spot, we can see that one of these vectors has changed. Okay, so over here in this position, we notice that Vy was like this and Vx was like that, okay, approximately. But here we see that Vy has now flipped over completely and is now a much smaller vector, but Vx hasn't changed at all. Okay, so I'm just going to trace out, this is Vy and that one is Vx. Okay, now if I let this go a little farther, okay, here we can see that now Vx is like this, Vy is like that. Okay, and one of these things is changing while the other one is staying the same. So watch, let me go a little farther. I'm sorry that we're getting some obscure, yeah, I'm going to go a little farther than that. Okay, now let's hit the ground. So I think it's pretty clear. Okay, if I were to run it again. Okay, hang on. Let me clear it. Run it again. Not sure what's happening. Oh, you run it again by doing this. Okay, so here we see the initial vertical component. That's V1y. And this is Vx over here. That's this component down here. Okay, now when I press play, okay, we can see that what's happening is the vertical component is changing over time. Okay, now look at the vertical component here, how small it is. But the horizontal one never changes, it's staying the same. And really that's the secret to answering projectile motion questions, right? Okay, so if that makes sense to you, there's one other thing that's important. If I change the launch condition, so if I reset this, let me erase all these lines that I've drawn. If I reset this and then change the angle, okay, and launch it again, okay, here we see a very different trajectory, so I'll try some different angles for you. Okay, look at that vertical component, how it changes as the object moves through. I'll put this one almost vertical. Okay, now for optimal range, 45 degrees would be the optimal range. Let's try that one. It'll go farther here at 45 degrees than it would with any other angle. Okay, and there you go. So here's several launches, but one thing that stays the same the entire time, okay, is the horizontal component of the motion. Now that component does vary with the launch angle, okay? And putting these two things together is how you solve projectile motion questions. So let's get right to it and let's see how we do that, okay? Now what I did was I posted on OneNote for you the keys to solving projectile motion problems. So this is just review, we did them last year. So here's the deal, we break them into two components, okay? And those two components are vertical and horizontal components, okay? And as we saw, you get a parabolic path. There are two components to the displacement, a vertical displacement and a horizontal displacement. Notice we're not talking about vertical distance that goes up and comes back down. We don't care about that. What we care about is the starting point and the ending point, vertically speaking. That would be a trajectory downwards in this case, like that, okay? All right, so there are 3 steps to solving projectile motion questions. And if you're wondering where these notes are, they're in OneNote. So please access OneNote to find these notes. And it says here, step A, make a table. Whoops, I'm gonna cross that out. Make a table with the headings horizontal, vertical, and launch. Decide whether down is positive. This is actually a crucial step. I always tell students, if the object is being launched upwards, you might want to make up as positive, okay? But you don't have to, it depends. If it's launched from the side of a cliff and it ultimately ends up below its starting position, you can make down positive. It really doesn't matter. As long as up and down aren't both positive numbers, you're good and you're not making a mistake, okay? Next, you populate the variables with the list of information that's given in the question. So you have to, your literacy has to be good here. You have to read the question and discern what information they're giving you. Now, what they don't have to give you is the acceleration due to gravity being 9.8 meters per second squared. They don't have to tell you that because you know that's what it is here on Earth, okay? Now, step C, use the 5 motion equations to solve for the vertical component. Now, you're not necessarily doing it in this order, step C, but in many cases, this is the order that you would do it in, okay? So use one of those equations. About 99.9% of the time, we don't care what V2 is, which is the impact velocity. And so we use that equation, okay, for the vertical component. Also part of this step, you use that equation for uniform velocity to solve the horizontal component. And then you use components to isolate the launch conditions, sine and cos components. I have summarized that for you here, okay? So the launch conditions are right over here. You very often do not have to use the tan theta equation, but occasionally it comes in handy, depends on the question. And then usually it's just the first 2 though. And here you populate this information, you fill in the blanks with all of this depending on the question, fill in these blanks, and then you solve for your unknown. What links the 2 equations? Time, whoops, I don't know how to spell that correctly. Time links the 2 vertical and horizontal components together. They have the same amount of time, obviously, okay? All right, so here I have an example for you. So you can read this for yourself, but what I'll do is I'll just go through it with you. So a baseball player leads off a game and hits a home run. The ball leaves the bat at an angle of 30 degrees. So right away, you read that question. We've made our table already. And right away, we know the launch angle is 30, which means Vx would be 40 times the cos of 30. So the speed is 40 meters per second. We see that too. And that makes V1y 40 times the sine of 30. And as soon as I make the decision that V1y is a positive number there, I'm saying up is plus. Up is plus. So I made that decision. Up is positive, which means gravity is negative. Keep that in mind, okay? Now, here's what we're gonna do. We read the question, it says, how far will it travel in the air? Okay, in other words, what is its range of this projectile? How far will it travel through the air before hitting the ground or before wherever it lands, okay? And here's the deal. We know that delta dy is 0 because we're assuming that it starts very close to ground level where you hit it, and it's going to land on the ground in the field somewhere. I know it says a home run, okay? But we're assuming this is not in a stadium where it's going to hit the stands somewhere at a vertical height. that's not 0, okay? But let's say it's in, you know, a field somewhere where outside the parameters of the baseball diamond is just more field. So it's going to land past the fence. So it's still a home run, but on the ground. So that means delta dy is 0. A lot of people don't get that when they read the question. But very often it's 0. It just depends on the way the question is worded. But in this case, it doesn't tell us explicitly. But we can assume it's 0 in this case, or at least close to 0. Okay, there'd be some small displacement when the guy hits the ball slightly off the ground, but if it's 1 or 2 feet off the ground over a range of a couple of 100 meters, it won't really make much difference if we include that 1 or 2 feet, so we can just assume it's approximately 0. All right, we're trying to find the time in the vertical component, and we don't care what v2y is. Don't assume v2y is ever 0, okay? So here's the deal. We go ahead and use equation number 3 from the uniform accelerated motion equations. Okay, we're solving it for time, which is the thing that links my 2 components. You don't need to use the quadratic formula when displacement is 0 because you can cancel out a t. Okay, and you end up with 4.9t equals 20 times 4.08 seconds. All right, now we move on to the horizontal component. We'll do this last. Here's our launch condition that Vx is 40 times the cos of 30, and we found our time was 4.08. So all we got to do is use this equation here, multiply them together, and you get a range of 141 meters. All right, so that in a nutshell is how you do projectile motion equations. These 3 steps here, okay, starting with the launch conditions first, okay. Second, we do the vertical component to find time. And third, we look at the horizontal component to answer the question and find range. That, in a nutshell, is how, generally speaking, you do projectile motion equations. Now, you might have to do the steps in a different order. It depends on what they ask you. In this case, asking us for range is whatever they ask you for is always the thing you have to do last. So in this case, the range, this number here, that's the last thing we have to do. Okay, so that's it for this lesson. I just wanted to show you at least one example. You give it a shot, okay? There is a tricky one on the assignment, but I want you to give it a try. You're in grade 12, you've done this before. So I want you to give a couple of tricky ones a try, and then we'll move on from there. All right, so I'm gonna stop this, and we will talk to you very soon.